In this video, we will introduce a very important fundamental result in calculus, which allows us to do lots of connection between the algebraic property of a given function and also the geometric property of such a function, the graph property, right? So one of the goals we want to achieve in calculus is given a function y equal to f of x. So let's assume it's a function. It's good. This is a function, right? There are two collection of properties, and for example, you can write on the graph g here to be x f of x, and right, x is inside the domain of f. Right, you get such a graph. In such a graph, without really sketch it, we want to know when the function is increasing. Increasing. We want to know when the function is decreasing. We want to know what's the what are the local extreme values, right? That's very important to decide. That's very important property we want to decide for an arbitrary function, right? With some possible applications. How do we do that? We are given a collection of derivatives and derivatives. We are given f prime, f double prime. So that's a given algebraic property of this function. We can decide when the function is positive, negative, or when the derivative is function or positive, negative. We can solve that. So we want to make the connection between the positive, negative sign of derivative or second derivative to decide whether you have a local maximum or local minimum, or increasing, decreasing. Later we'll introduce concave up, concave down. Some nice geometric property of the graph, right? For sure it has its meaning and it's very important. So the foundation to make all the connections is the mean value theorem. So the mean value theorem, MVT, right? Mean value theorem. So let's say that let f here be a function satisfying the following. First one here, f has to be continuous. F is continuous on the interval AB, right? This is a closed and bounded interval. Second condition here is f is differentiable on the open interval on AB. So this is closed, right? This is closed. Sorry. This is closed. And this one here is open, right? Which means the terminal points, endpoints are excluded. And so what's our conclusion? The conclusion here is then there is at least, right, C the number inside AB such that what happens is we can make a connection between the derivative and the function value. So what's the connection I made? Which is f of b minus f of a over b minus a, right? Let's try to use a picture to illustrate what is going on, right? We have our y-axis, we have our x-axis, we have our point, let's call that a here and b here. And then we have a function, which is very nice, right? Function like a function like this, right? Okay, so that's a function which is y equal to f of x. So this is b f of b, and this is a f of a, right? So f of b minus f of a over b minus a, that's basically the slope of this secant line, right? So you have such a slope, right? This is basically the slope of the black line, right? So our conclusion of the mean value theorem is you can always get a tangent line, get a point, which is parallel to the secant line, starting from a f of a to b f of b. Right? They are parallel, which means so slope is f prime of c if you have this is a point, right? And the slope of the black line, black secant line slope is f of b minus f of a over b minus a. They are parallel to each other, so which means this should be f prime of c. So that's the mean value theorem, right? So this is basically the foundational result, which makes a connection between what between the algebraic property of the function and the like increasing, decreasing local extreme values, and later we'll discuss concavity also. So that's basically this result guarantees we can do that, right? So let me write down a very straightforward application of the mean value theorem, right? So let's see that. Fact one here, right? So if f prime of x is always positive for all x inside AB, then f is increasing on AB, right? Let's recall the definition for increasing. Increasing means f of x1 less than f of x2 whenever you have x1 less than x2, right? Function value is getting bigger and bigger for all x1, x2. If you have x1 less than x2, they are both in AB, and the f of x1 has to be less than x2, right? Let's see a justification using mean value theorem, right? This is, you can see that this is the result we are interested. The algebraic property of the derivative give you the geometric property of the function. Function is getting larger and larger. The curve is going up, right? So let's see that. You want to show this is true. Right? You want to prove whenever you have x1, x2 inside AB with x1 less than x2, then f of x1 is less than f of x2, right? What do you do here? Just take a pair, right? Take x1, x2 inside AB with x1 less than x2, right? Take a pair. You want to show that f of x1 is less than f of x2. Now, how do we do that? We want to use mean value theorem. So you can use mean value theorem on the interval from x1 to x2, right? So clearly, because the function is differentiable, because we say that differentiable implies continuous, right? Clearly, f here is continuous on x1 to x2 and differentiable on x1 to x2. So apply mean value theorem, and there is a C inside x1, x2, such that f prime of C is f of x2 minus f of x1 over x2 minus x1, right? So this is basically a direct application of the mean value theorem, right? Just with AB to be x1, x2, right? So, okay, we know that the derivative here is positive. So which means f prime of C is positive. So f of x2 minus f of x1 over x2 minus x1 is positive. Because x2 is greater than x1, so we get f of x2 minus f of x1 must be positive. So I dot E, you get f of x2 greater than f of x1. So the function value is actually getting larger and larger, right? So that's basically how do we apply the mean value theorem and to show that if you have a function in a interval, the function has positive derivative, then the graph is going up. The function value is increasing, right? Use very similar discussion. We get another two fact. Fact 2 here. Fact 2. If f prime of x is less than 0 for all x in AB, then f is what? Is decreasing on AB. Another very important one here is 3. If f prime of x equal to g prime x for all x inside AB. You have two functions. They share the same derivative, right? Their derivatives are identical, right? Then they are closely related. Then f minus g is a constant function. So one function is another function plus a number. So if they share the same derivative, you can get one from the other by plus a constant.